Hello everybody, we will continue with our lectures on optimal guidance, control guidance and estimation course. We are in lecture number 2. The very first class we saw some overview and then some motivations of this course, and this particular lecture will have some overview of state space approach and a little bit overview of matrix theory. So, these are the two things that we use it very extensively here in this course. So, I thought we will just have a overview of that, and I assume that you must have already taken some course on this subject. So, this is just to kind of refresh your knowledge on that. So, let us start with state space representation, very basic ideas and all that. So, when you talk about any system, dynamical systems, we typically talk about 3 types of variables. One is input variable, and the other one is output variable, the third one is state variable. And I kind of discussed that in the first lecture also, and typically the input variable can be classified into 2 classes. One is manipulative, which is control variable, or it can be non-manipulative, which is noise, and remember both are input to the system anyway. And then considering output variable, that can be defined as either the variables of interest or that can be like some measured variable or calculated variable. So, these two may or may not be same, and this is what the diagram it tells. See, in other words, your performance output can be y, and that you want to drive it to some desired value y star, whereas the measurement output can be z, and that may go into the controller, and then control design can take place actually. So, it may be so happening that part of the y variables or full of the all of the y variables can be part of z and vice versa probably, but they need not be same actually. Okay, so, all these things can be talked about in a standard state space class and all that. But anyways, coming back, there is also some class, this variables of great importance is state variable, and that is defined as minimum set of parameters which completely summarize the system status. And more definitions, more implications and things like that can be found in a standard textbook on systems theory, and any modern control book will kind of give you more insights with examples and all that actually. But we understand what it is, what we mean by state variable, and that means a minimum number of variables which can describe the system state. And obviously, remember that you cannot take more than the state variable that is required, or you cannot take less than the state variable that is required either actually. Okay. So, that is those things are kind of known to us actually. Now, continuing further, we have broadly 2 classes of systems that we discuss about here, and one is nonlinear systems, the other one is linear systems actually. And when you talk about nonlinear systems, we represent the state equations this way: x dot equal to f of x u. Typically, time variable t is not there, where x dot represents derivative with respect to time. And remember, state variable dimension of state is Rn, that means n number of states are there. Control can be Rm, control belongs to Rm, that means u can be of m dimensional, and the output that of interest can be of p dimensional actually. And also this R, letter R represents real numbers. So, we are typically deal with all real numbers here. And nonlinear systems as we know are typically little bit difficult to handle and difficult to analyze, synthesize, all that. So, most of the time we linearize the system about some operating point and all that, and then end up with some representations like that, where x dot equal to x plus b, y equal to c x plus du. But remember, this x what you see in nonlinear system and this x what you see in linear system, the meaning wise they are different. When you talk about state of nonlinear system, it is actually the true state, whereas the state of linearized system, most of the linear systems are anyway linearized. So, the linearized state and control are typically deviation variables actually. So, that means x represents delta x and u represents delta u implicitly here, and delta x can be the deviation of the state from its operating point, and delta u can be the deviation of control from its operating control and all that actually. Okay, so, those kind of definitions are available. So, in this particular course, we will deal both with linear system as well as nonlinear system. We cannot, we are not talking about only one class of things, we will deal with both of the things together actually. And coming to the state variable selection, typically the number of state variable, that is the order of the system, is equal to the number of independent energy storage elements. Okay, but there are exceptions as well, you can see couple of examples. in probably in some standard textbooks like Norman Nice and all that will give you that actually. Yeah. But is there any restriction on the selection of the state variable? I mean, the answer is yes, and the very primary requirement is all the state variables should be linear independent, and then all of them must collectively describe the system completely. I mean, that is these are the two things that the state variable should have actually. Okay. Now, coming to the linearization of nonlinear systems, see, remember that that's what I told you here. The linear systems are typically linearization of nonlinear systems about some operating point actually. So, how is it done? I mean, how is it done? Let us see that. The problem statement here is given a nonlinear system like this x dot equal f of x u, can you derive an approximate linear system about an operating point x 0 u 0? The approximate linear system can be described something like this actually. And also remember, when you talk about operating point, typically the misnomer is it's an equilibrium point, but need not be true actually. So, operating point by definition is a point through which the system trajectory passes. That means, even if it is passing through a transient trajectory and all that actually, that can be a potential operating point. And so, that is how sometimes we linearize the system about a trajectory continuously, we keep on getting a new linear, I mean linearized systems, that means the A and B matrix will become time varying and all that actually, if you do that. But if it is a equilibrium point, that is your operating point, and then you linearize the system, then you will end up with A and B being constant matrices, and these constant matrices, that is why you will get into this so called linear time invariant systems and all that actually that way. Okay. But remember, the operating point is a point through which the system trajectory passes, that is the definition actually. Okay. And obviously, if a equilibrium point is also a point through which system trajectory passes, because if it is a stable system, ultimately the trajectory will come and sit there. So, that is also a possibility of an operating point actually. So, anyway, so these are the ideas there. The key point to note is even though we represent the same state notation, state and control notation x and u, when you talk about linear systems, by definition this state is actually deviation state and this state is actually deviation control actually. All right. So, proceeding further, how do we get it? That is through this Taylor series expansion and all that. So, you have a system, nonlinear system, where we have a reference point here, something like x naught u naught. So, if you put the x equal to x naught plus delta x and u equal to u naught plus delta u, and then this side of the story f of x x u can be represented like this, and then you use the Taylor series expansion when you can expand it something like a first term, a constant term, followed by two linear terms in state and control, then these higher order terms. So, if you, and also remember, the operating point is a point through which the system trajectory passes, that means this x naught u naught satisfies the differential equation. That means, if I substitute x 0 dot x naught dot, then that is nothing but f of x naught u naught. So, this is what is exploited here. Remember, this side of the story is like this. So, but that side of the story will be something like that, like x dot equal to x 0 dot plus delta x dot. So, that is nothing but equal to this right hand side, okay, neglecting the higher order terms, it is approximately equal. And then we take, okay, these two will cancel out, because this is what the operating point is all about. These two will go, okay, and then you will end up with this x naught equal to then you will end up with this x naught equal to I mean delta x dot equal to a times delta x plus b times delta u. But instead of writing down all the time delta x and delta u things like that, we implicitly redefine it as delta x equal to x and delta u is u. Then this leads to x dot equal to x plus u. That is how this x and u represent this delta x and delta u, I mean that way. But also, I mean if x naught u naught happens to be 0 0, then obviously this delta x equal to x and then delta u is also equal to u basically. So, these are the corollaries and all that. And remember, A and B will be defined in terms of this Jacobian matrices that way. So, you have this state equation with the system model is available to you. So, expand these partial derivatives that way and then put them in a matrix form and evaluate at the point of x naught u naught actually. That is what you will do for A and B matrix. A happens to be n by n square matrix and B will happen to be n by m non square matrix in general basically. Now, coming to, so now if you will end up with some system equation like that and try to carry out a lot of algebra and then optimal control synthesis and things like that, obviously we have to deal with these matrices A and B. So, we have a lot of requirement for matrix and algebra on the way actually. And also we will deal with, even if you deal with nonlinear system, we have to deal with gradient matrices and all the gradient vectors and things like that. So, we certainly need the concepts from matrix theory actually. Let us have a quick overview of matrix theory in general, and then we can from next class onwards we will go to optimization theory or little bit overview of numerical methods as well before you go to optimization theory and all that actually. Anyway, so coming to the review of matrix theory, so let us start with very simple definitions. We all understand what is meant by matrices, so I am not going to that level. It is a collection of numbers in an array and things like that. But coming to some definitions, standard definition, a symmetric matrix is represented as something like this. When A is equal to A transpose, then obviously A satisfies the property of symmetricity. Now, when determinant of A becomes 0 and here we assume that A is a square matrix, then we talk about well, the matrix is a singular matrix actually. That means inverse does not exist actually. Then what is inverse? Inverse of a matrix A and B, I mean if B is an inverse of A, then this satisfies this property. A B equal to B is nothing but identity basically. So, that is how this forms the definition. And then as a standard result, A inverse turns out to be adjoint of A divided by determinant A. And again I emphasize here that do not get confused with what is definition and what is a standard result actually. As far as definition is concerned, I will put this is a definition, okay. A B equal to B A equal to identity, and lot of these theorems proof and then general results and all will be very easy to do using this definition A B equal to B A equal to identity. However, if you really want to compute an A inverse for a matrix and all, probably that is the standard results that we typically use also many times. Even though it is not very computationally efficient way of computing A inverse by the way. So, that is the difference. It happens to be like one and the same. In other words, both are if and only if condition sort of thing. So, sometimes people get confused that A inverse definition is this adjoint of A divided by determinant of A, but in definition sense this is the definition and this happens to be a standard result actually. Now, the next concept is what is called as orthogonal matrix, and orthogonal matrix happens to be something like okay. Orthogonal matrix happens to be something like this way. So, if A transpose equal to A transpose A equal to identity, then it is an orthogonal matrix actually. Okay. And also remember that A times A transpose and A transpose A are guaranteed to be kind of I mean square matrix, even though A is a non-square. And on top of that, you can also show that A transpose A and A transpose both happens to be something like positive semi-definite matrix and things like that. It's not that difficult to show actually. But anyway, in addition to that, if they satisfy this property that A transpose equal to A transpose A equal to identity, then the matrix A is called as an orthogonal matrix. And one property of orthogonal matrix is like this: if a matrix A is orthogonal, then all its columns are supposed to be orthonormal vectors actually to each other. So, I mean that is a vector sense basically. That means, if you have a matrix, if you have a matrix of some matrix which is given by some columns and all that way, and then each of the columns that you see here will be orthogonal to, rather orthonormal to each other actually in a vector sense. So, the typical example is something like this. This is a very standard what is called as a rotational matrix. That means, if you have a point, then the representation turns out to be like this. Okay. If you have something like this coordinate frame and things like that, you have this x versus y coordinate frame and you have a point where x y is there, and then the question here is, if the coordinate frame rotates by an angle theta, let us say, that means you have y prime and x prime y prime, this is again angle theta, then in the new coordinate frame x prime y prime, what is the the values of this coordinate x prime y prime. So, then that is kind of given by this transformation matrix and all that. That's why it is called a rotation matrix. If you take a coordinate in the original coordinate frame and multiply with this, pre-multiply with this matrix, then whatever number you get, that number happens to be your coordinate in the new coordinate frame actually. Alright, and this result I have already told you that the columns of an orthogonal matrix are nothing but they are orthonormal to each other in a vector sense actually. Okay. Then next concept is eigenvalues and eigenvectors, and this is how we can think of interpreting it actually. Now, this is a common mistake that people take. Okay, if it is a eigenvector, then I mean there is a standard equation for that, and then I will solve it. And especially about eigenvalues, a minus lambda is determinant equal to 0, and then I will get values for lambdas, and that is nothing but eigenvalues and all. So, that is a standard result again, but the concept can be understood something like this. Let us start with a simple understanding here. So, let us take a point P in a coordinate frame x and y. So, and talk about this, let us say this is something like x1, x2. Okay. So, the coordinate frame happens to be something like okay, whatever this is the I mean horizontal, and that is the vertical coordinate frame you can think of in general. Yeah. Okay. So, you have a point P, okay, and that is x1, x2, okay, originally, and we multiply that by a matrix, okay, some matrix A. Then we will end up with some numbers y1 and y2, and that y1, y2 can represent a point in the coordinate frame something like q. That means, if I join this origin to this point P and the origin to this point q, then I am actually getting two vectors. Okay. Now, if you look at it slightly closely, then it turns out that by multiplying this vector x1, x2 by a matrix A, what I have done? I have transformed this point P to Q in general. In a way, what I am doing is I am actually taking this vector and then rotating it as well as stretching it. So, there is a stretching and rotation operation involved basically. So, any matrix multiplication is matrix are also called linear operators by the way. So, any matrix multiplication with a vector will give you another vector, and that vector need not contain the same magnitude and same direction actually. So, it can act as something like a stretching operator as well as a rotation operator. Now, the question here is something like this. Okay, it may not happen in general, but suppose I have a vector x some direction somewhere, okay, and I multiply that with matrix A, I get another y which is aligned along the x axis, I mean this vector origin to x vector and is aligned there. That means, this matrix is operating only as a stretching vector, not as a rotation operator, but as simply as a stretching operator. So, that means it does not affect any other direction, it just takes the vector x and then just stretches it along further actually, and stretching by definition can mean shrinking also. So, that is also a possibility actually. So, that is the question you are asking actually. So, in other words, does there exist any vector x, some vector x for a particular matrix A, so that this operation A times x will give us a vector y which is nothing but a stretched value of vector x basically, that is all we are talking. So, in other words, if you think about that is how this all starts actually. So, you are asking some equation like what are you asking? If y is nothing but I can interpret that y equal to nothing but lambda x sort of thing, okay. But y is also a x, remember that. So, what I am getting here is a x equal to lambda x, that is how the eigenvalue and eigenvector equation is defined actually, okay. So, y is nothing but lambda x, that means that is a stretching operator, and y by definition is a times x anyway. So, that is how you get a into lambda x actually. So, that is how you get it, but then the solution, the question is when can we have a solution to this equation, and that solution to this equation obviously turns out that okay, if that is true, and that has to be true as well, lambda I minus a equal to lambda I minus a whole multiply with x equal to 0. And if you really need to have a non-trivial solution, that means remember this equation is invariably true if you have 0 0 0 0 as x vector, that means it is a very trivial thing, we are not moving anything away from the origin actually. So, other than that, if you take any other thing, then for this to have a meaningful solution, a non-trivial solution, we should have this relationship satisfied. That is a standard result from linear system of equations actually. Yeah. That is how this equation comes here actually. Yeah. So, this is if you take this equation, remember determinant is a scalar operator. So, you get one equation, but then this can be a nth order algebraic equation. That means, you can have n solutions and all that actually. Okay. So, that is how you get if the matrix is of a dimension n by n, then you will end up with something like n equations, I mean nth order equation, and hence you will have n eigenvalues. And because these coefficients will be real numbers, you will end up with either real numbers as solutions or complex conjugate as solution. You cannot have a single complex number hanging out actually. So, that is that's a standard result again actually. Okay, where do we use these concepts? Okay, by the way, how do you evaluate eigenvectors and all? Once you evaluate the eigenvalues like this, you go back and put it there. But remember, it does not give you some sort of like a unique solution. It may give you something like an under constraint equation, and hence you will have infinite solution. But also remember, eigenvector by definition, they do not have any magnitude. That means, you are happy with only the direction of that. Okay, so that and then sometimes we do this normalization of the vector and tell okay, normalize eigenvector and all that. But by definition, eigenvectors do not contain or do not have any magnitude associated with them actually. Anyway, so this is how it is. Where is the utility? Utility of this analysis is huge. It is used in stability and control analysis. It is used in optimal control synthesis of linear systems anyway. It is also used in model reduction, principal component analysis, and the variety of other applications in almost every field of engineering actually. So, that is how the importance of this concept comes actually that way. Now, there are certain very standard results that come handy also, and one of the few results, I mean very standard results, I will just take it through. So, in other words, this standard results tells you that if you have lambda 1 to lambda n as eigenvalues of matrix A, which is of n by n, then for any positive integer m, you really do not have to evaluate this a to the power m and then go through this equation and all that actually. The result tells you that if I have a to the power m, then that eigenvalues of a to the power m will satisfy this relationship. I mean, all that I have to do is just to take it, just to kind of find the individual powers of these values, and I am done actually. And it is very easy to show that from a proof sense also. In a second order sense, I will show that. So, you start with something like lambda x equal to lambda x, that is how it will lambda will satisfy eigenvalue property of matrix A. Now, just that you do multiply both sides, okay, that you will get A into lambda x, okay, A into, okay, sorry. Okay, as you will get A into lambda x, and then if you go through that, and then this turns out to be something like A square x equal to lambda times A x, and lambda times A x is again you know this lambda times sorry, A x equal to lambda x. So, that then you will end up with lambda square x. So, A square x is nothing but lambda square x sort of thing actually. So, that means it tells you that lambda square is an eigenvalue of A square. So, that is very standard, and then you can keep on repeating this exercise to get higher powers as well actually. Okay. Okay. So, let us continue. Then the next one, it is very easy to show that again, that if what about A inverse actually. So, remember A inverse is a computationally expensive operation. So, we really don't want to carry out inverse operation unless otherwise it is badly necessary. And also turns out that if I know the eigenvalues of A matrix already, then the inverse matrix A inverse, that will have eigenvalues as something like nothing but lambda inverse, that means 1 by lambda sort of thing actually. So, they are eigenvalues of A inverse. Again, very easy to show that by simply taking A inverse, multiplying both sides by A inverse actually. You will end up with x here in the left hand side, and then it will be A inverse in the right hand side, and then you will very easily show you can take 1 by lambda into x equal to A inverse x sort of thing actually here. So, you can do the algebra yourself and you will get convinced in just takes 2-line algebra actually to show that. Okay. And the third property that comes to mind is for a triangular matrix. Remember, it can be either upper triangular or lower triangular, and of course, diagonal matrices are special cases of that as well. And for such matrices, the eigenvalues are nothing but diagonal elements actually. It is extremely easy to show that again starting from this equation. If it is if this equation will not get perturbed anywhere else, you will just simply deal with these diagonal elements, and hence you will get something like, I mean, very easily you can show that it will be multiplication of lambda minus well, the diagonal element a11 lambda minus a11 into lambda minus a22 into lambda minus a33 like that, all that thing equal to 0, and hence lambdas will be nothing but a11 a22 a33 like that actually. All these happens to be diagonal elements actually. So, this is how it again it can be shown this way. Now, coming to this some of these other properties, and this happens to be quite useful property actually, that if some I mean symmetric matrix, not symmetric, if a square matrix is symmetric, okay, the theorem talks like this, that if a square matrix is symmetric, then its eigenvalues are all real, and remember eigenvalues can in general be either real or complex conjugate pairs actually, but this theorem tells you that all that is necessary for this theorem is that matrix needs to be symmetric. And if you have a symmetric matrix, its eigenvalues are guaranteed to be real actually, and that can be proved also. It is a little bit involved proof, but it can be shown with not that much of a difficulty either actually. And the theorem again tells you that not only that, moreover it has n linear independent eigenvectors. So, these are a beautiful property of a symmetric matrix. So, whenever we do not have a symmetric matrix, we will rather try to decompose that in something like I mean a combination of symmetric and then skew symmetric matrix and all that actually. But that is a, I mean those things are standard results in linear algebra anyway. But it talks, I mean this, just notice that I mean if you really know that a matrix is symmetric, then you can very quickly conclude that eigenvalues are real and it has n linear independent eigenvectors as well actually. Very beautiful and very powerful property actually. So, I certainly urge you not to forget this that way. And this next theorem tells you that if a square matrix has n real eigenvalues and n real orthogonal eigenvectors, then the matrix is symmetric as well. So, this is kind of a counter theorem for this particular thing actually. Okay. This theorem tells that if a matrix is symmetric, then this thing happen. The question is when the other thing, reverse thing happens actually, and the answer to that is here, that if a matrix has n real eigenvalues and as well as n real orthogonal eigenvectors, then only the matrix is symmetric. So, that is property, something like a converse theorem basically. Then the next one talks about something like this: A transpose A and A transpose are always positive semi-definite matrices actually. Okay. It's again it's very easy to show, it's not that difficult at all. So, if you have A transpose for example, okay, what is positive semi-definite and all, I think if you, if it is here actually, let us go there and then we will go back to that. So, by definition a matrix is said to be positive definite provided I mean it satisfies this relationship, that if I carry out this operation x transpose A x for any non-trivial x, that means x, all that is necessary is x is not on the origin actually, x is not equal to 0 0 0. I take any real number, I mean any value for x vector and simply carry out this algebra, the x transpose A x. Okay. So, this x transpose A x, remember it is 1 by n times n by n times n by 1, that means it is actually guaranteed to be a scalar quantity. So, this scalar quantity, if it is greater than 0 for all such x, okay, then the matrix is called as positive definite. And if you can tell only this much, that it can be either positive or equal to 0, okay, greater than equal to 0, then it turns out to be positive semi-definite. And similarly, if it is strictly negative, then it turns out negative, and less than equal to 0, it turns out to be negative definite. And again remember, this side of the thing is definition, and that these definitions are tightly related to these properties. But many times again we take these properties as the definition, when we forget that this is true, this is where it comes from actually really. So, whenever there is something to show and things like that, I certainly urge that you carry out operations along with this definition ideas actually, that will be much easier. But when you want to evaluate and if you know some values, some properties of eigenvalues, I mean some values of eigenvalues and things like the numerical values, then looking at those values you can also conclude whether the matrix is positive definite or not and all that actually. But anyway, coming back to this, the claim here what I told is A transpose A or A transpose, both are always guaranteed to be positive semi-definite at least. Now, it is very easy to see that A transpose is guaranteed to be a square matrix, no matter whatever, whether A is a square matrix or not. Now, all that both actually, I mean both A transpose A and A transpose are guaranteed to be positive semi-definite. Now, all that you need to show, that suppose I want to show this as a positive semi-definite, then by definition I have to do this operation, where for all non-trivial x, and that turns out to be, this is similar anyway. So, let us not worry about that, just carry out this one. This turns out to be x transpose A transpose into A x, okay, and this is nothing but, if you take this transpose property and all, this is nothing but A x transpose times A x. And if you define y, remember A x is nothing but as a vector actually, A x is a vector. So, I can define that as y. So, essentially this I will end up with something like y transpose y, and that is if you think a little bit carefully, this is component sense, it is going to be something like y1 square plus y2 square plus yn square or something. Okay. So, this is guaranteed to be greater than or equal to 0. Okay. All these are summation of quadratic terms and things like that. So, it is very easy to show that this A transpose A is guaranteed to be positive semi-definite at least actually. Okay. And there is another result which tells you that if A is a positive semi-definite matrix, then every principal submatrix of A is also a symmetric and positive definite. Okay. In particular, the diagonal elements of A are guaranteed to be positive actually. Okay. So, because we talk this is a concept of submatrix and things like that, but remember, if somebody tells us that there is a positive definite matrix A, then the diagonal elements of A are certainly going to be positive. So, that is a property that many times we use actually. So, this is I have already told, when what is defined as positive definite, positive semi-definite, negative semi-definite matrices actually. Then there is another concept called vector norms. Again, we use it heavily in optimal control theory as well. And vector norm is defined something like that. It is a real valued function. That means the output is always a real number, which satisfies the following properties again. That means, if I know a vector x, the norm of vector x can never be, never be negative, and it's most of the time it is positive. It is 0 only if x is a trivial vector 0. That means, only if x is 0 0 0 0, that origin point rather, then only the norm is 0, otherwise it is always guaranteed to be positive. Essentially, the norm is nothing but the concept of distance actually, distance from the origin and something like that way. So, distance from the origin is 0 only when you are at the origin itself. Okay. Anywhere else the distance is certainly going to be positive, that kind of thing actually. It also satisfies the second property, okay, alpha times x. If alpha is a scalar, if you take the norm, it will satisfy modulus of alpha and times norm of x. That means, it does not matter the sign of alpha really actually. So, whether alpha is positive or negative, it is guaranteed to stretch it actually that way. Then there is also a triangle inequality result, which tells you that if I take vector x and vector y and I sum it up and then take the norm, that is going to satisfy this this less than equal to norm x plus norm y actually. So, that is the concept of vector norms, meaning of having a distance actually. And some standard results, there are various norms which can be defined for computation purpose, and the first thing that comes to your mind is one norm. So, that means, you just simply take the components and then take the kind of absolute values and sum it up. There is nothing but one norm. Two norm is something very standard, we all know that. Okay. So, we just take squares of everything and then take half, and obviously, here you can always argue that modulus is not necessary, true, but to have a systematic way of definition, we take modulus everywhere just for math sake actually. Then if you have norm 3, you can do the similar algebra, take third powers everywhere and then take 1/3, and similarly the pth norm in a standard notation sense, it can be defined that way. An infinity norm turns out to be like this, going by this definition, and it can be shown, it is an interesting kind of result actually, that even though infinity to power and 1 by infinity and things like that are there, it is essentially, it has a meaning, and it turns out to be that the maximum value of this modulus of xi. That means, if you simply take this modulus thing and do not add it up, just look at the values and see which is the maximum value, okay, and that value is nothing but infinity norm actually. And very interestingly, it turns out that in finite dimensional vector space, so that means the dimension is really not infinity, in other words, X has some n components only, it does not keep on containing many terms. So, I mean infinity components really. Then in finite dimensional vector space, all norms are something like equivalent. That means, if you prove something using some norm, whatever norm is that, and some sort of a similar property will hold even if you talk about any other norm actually. Okay. So, this is the standard property in finite dimensional vector space actually, which is not true in infinite dimensional space actually that way. Okay. Now, moving on further, there is a concept called matrix norm as well, and the matrix norm turns out to be something like that. Again remember, A times X is nothing but a vector. So, A times X is an operator basically, it transforms the vector X to vector Y basically that way. We have seen that little before. Now, the question is, if you let us go back to that diagram, and here if you have a X and this is like a stretching operator, even in general its vector gets transformed P to Q and there is a stretching operation involved there actually. Okay, so in that context, the question here is, if I multiply any vector X with matrix A, then I am getting a vector Y which is a different different magnitude and things like that. Now, the question is, how much does it get stretched because of A, not because originally the vector itself was longer or shorter. We are not interested in that. So originally it can be longer or shorter. Okay, then we are not interested in that kind of thing. We are telling that if I multiply a vector by matrix A, then I get some vector, and the question is, how much I am stretching the vector. Okay, how much I am stretching the vector because I multiply it with matrix A. That's the question actually, and that can be argued that okay, I can evaluate it this way. That means, I evaluate the norm of Y and divide it over again by norm of X actually. Okay. So, this is something like that. So, that is how it is evaluated. Remember, this vector norm, both these numerator and denominator are vectors, and vector norms are already defined here. So, you have to pick up any norm, that norm, first norm, second norm, third norm and all that, and then you can talk about carrying out this algebra, and it turns out to be it is actually defined some sort of amplifying factor or amplifying property of this matrix actually. So, that is how it is defined as the matrix norm actually. It is also called operator norm, induced norm, things like that, various terminologies actually. It is also true that if instead of carrying out this algebra, if I constrain myself to this norm equal to 1, then obviously this is 1, norm of X equal to 1, and hence all that I have to see is what is the maximum value it takes actually. Okay. And remember, there is a maximum operation involved actually. That means, I have to carry out something like I have to see a family of X, all sort of X actually, whatever is there, and then I have to take a maximum value whatever happens to be there. So, maximum amplifying property that comes out of a matrix actually. So, instead of this algebra turns out to be a little bit tougher because there will be infinite possibilities and all that. So, we confine ourselves to this constraint, that norm of X equal to 1, and then carry out something like a maximization operation, maximization analysis and all that, and tell okay, this is what the value is actually. That is how it is defined. Again, property sense, it will satisfy some of these properties. So, that norm of A has to be greater than 0. It is 0 only if the matrix A is like nothing but a 0 matrix. All the elements of matrix are 0, then only it will happen to be like that. And for that properties B and C are extremely similar to what we saw in the vector norm sense. Okay, and then it turns out that okay, there is additional property that if I multiply A times B and then take a norm, then it turns out to be less than equal to norm A into norm A as well actually. This is a property that doesn't it is not there in vector norm, but is there in the matrix norm actually. So, I hope it is slightly clear now that all that we are talking in a matrix norm is looking at the amplifying property of matrix itself basically, and we take how much maximum it can amplify for a vector X actually that way. So, that is the concept, and these are some of the properties involved. So, again computational sense, how do you compute first norm, one norm if you tell okay, this is the definition, that means you take all the elements of the matrix and then kind of take all the these absolute values, and then all that you have to do is formulate this column sum and all that. So, let me just just to demonstrate that. So, this is something like okay, if I have a matrix A and then talk about something like entries everywhere, all that I take is just absolute values of everything, all the elements whatever I have, and then I can do a summation here, okay, this way, okay, or a summation that way, either way, okay, and then take, okay, if I see the summations here and see whether out of these 3, I mean 3 or whatever values are there, which is the maximum, or I can also tell, okay, which is the maximum here actually out of all the 3 things. So, this is what the concept, one is the maximum row sum and one is the maximum column sum actually. This is what is talked here, and it turns out to be the largest absolute column sums, it is your first norm, okay. If I take column by column, okay, and then see the values here, and then end of the columns actually addition of all the values, and then tell, okay, what is the largest value among those possibilities, that is nothing but your one norm. And similarly, infinity norm turns out to be the largest absolute row sum as well. Okay, that means you do not carry out the column sums, but you carry out something like a row sum, and then see what turns out to be in the right hand side, and then tell, okay, what is the maximum value out of that. That turns out to be infinity norm. And just a hint of note, I mean, so how do you remember these two? Letter 1 turns out to be vertically, I mean, place. 1 turns out to be a vertical notation, and the infinity turns out to be slightly horizontal notation actually. So, using that probably you can think of carrying out algebra. But also we take 2 norm many times in analysis and then synthesis, and the 2 norm turns out to be some concept called maximum singular value of A. Now, what is singular value? We will see that. And remember this matrix norm and all, when you talk, the matrix need not be square. It can be, I mean, it can be a rectangular matrix as well actually. And singular values are also defined for rectangular values. Eigenvalues are not, by the way. So, singular values can be defined like that. Remember, A transpose A is always guaranteed to be symmetric. So, we can talk about eigenvalues of that matrix. And then remember, A transpose A is also guaranteed to be, I mean, positive semi-definite. So, the eigenvalues are guaranteed to be either 0 or greater than 0. So, we can talk about a square root of that, and then take only positive square root of that and define that as singular values. And in general, it is defined something like this. This A star, when you see somewhere, this it turns out that if your A matrix itself contains these complex numbers and all that, then this is this complex conjugate values and things like that. Conjugate transpose actually. You take complex conjugates and then take a transpose. This will satisfy many properties similar to A transpose. So, if you simply take transpose using these complex numbers and all, it will not satisfy what we know as transpose in real matrices actually. So, most of the algebra will be very compatible when you do this A star operation, where nothing but you take the complex conjugates and then take the transpose actually, conjugate transpose. Anyway, so this is the idea there. You carry out this algebra, take the eigenvalues of this matrix is guaranteed to be positive greater than equal 0, take the square root of that and you will end up with the singular values actually. Alright, so then there are concepts for least square solution and all that. So, the question here is something like this. If the I mean, there is an equation, linear system of equation Ax equal to b, and then we are asking for solution for x actually. Okay. Now, in our previous knowledge and all that, it is very standard that if m equal to n, that means it is a square system. A is a square matrix and you have equal number of variables as number of equations. Then there is a unique solution x equal to A inverse v. Okay. It's a very standard result, we all know that. But the question is, what if A is non-square matrix? Okay. So, that is where let us see the standard results here, and if it is non-square, then either m can be less than n or m can be greater than n. And here you are talking about m is less than n, that means number of equations are less than number of variables. Certainly something like an under constraint problem. And if it is under constraint problem, obviously we can think of having a solution which will satisfy the equations exactly, and in addition to that we can do something else actually, because we have more freedom and we have less constraints. So, we can think of a solution, in fact it has infinite solution which will satisfy the equations exactly. Now, out of the equations, out of the solution that satisfy the equation exactly, what kind of solution that are of interest to us actually? So, obviously one answer to that is minimum norm solution basically. That means, suppose you are talking about x being a control variable for a second, then we want to have a solution for this, for which we will apply minimum control really basically. Okay. Because we are not compromising anything on the solution quality, solution is certainly satisfied exactly, but we want to satisfy that with minimum control value as well actually. So, that is how we can think of the utility part of it.
So, that is how it is formulated, and the solution turns out to be something called pseudo inverse, Ax equal to A pseudo inverse B, and then it is something like pseudo inverse is defined like this. And also we know that pseudo inverse can be both right pseudo inverse or left pseudo inverse, and in this particular example it turns out to be right pseudo inverse actually. Okay. So, this is how it is. Remember, this solution will satisfy the equation exactly as well. Okay. So, under constraint problems are typically luxury in a way basically. Then what if there is a over constraint problem, exactly the reverse case where the number of equations are more than number of variables, and obviously in this case assuming that all these constraints are linearly independent, that means all these constraints have meaningful constraints and not some combination of other constraints and all that, then it turns out that we cannot do a perfect job, we can never aim to satisfy the solution exactly. But if you cannot do that, the next best is how can you get a solution which will approximately satisfy this equation. Okay, so that is the formulation here. It talks about minimizing the error quantity, second norm of the error quantity. Remember, Ax equal to B is the equation. So, Ax minus B is the error sort of thing. So, if you talk about that, then it is nothing but minimization of the error associated with all the equations actually. And interestingly, the solution again turns out to be pseudo inverse B. Okay. But this time this pseudo inverse is defined something like this, it is called left pseudo inverse, and sometimes it can be argued this way also, it is very easy to see that. So, if you have this something like Ax equal to B, then all that you do is multiply A transpose both sides. Okay, so you will end up with that, and A transpose A comes from here. So, you will end up with A transpose A inverse A transpose and B. So, that is you can interpret that way as well. So, easy to see that actually, but you will not be able to do this exercise that way that easily in this case actually. It requires a little bit further algebra actually. Alright, but the point to note here is this solution what you are getting here will not satisfy the equation exactly. Okay. It will satisfy only approximately that way. Alright, so this in general this is the left pseudo inverse, this is the right pseudo inverse, and some of the properties that pseudo inverse satisfy is something like that. And you can see very closely it will feel as if it is a inverse actually. If I talk about A pseudo inverse A, that means if I close the bracket here or close the bracket here, it feels like identity actually. Okay, so, that means it is A. And similarly, if I take the other operation, if I say this bracket or close this bracket and interpret the pseudo inverse as nothing but inverse, then I will end up with the other one actually. Okay. So, it will feel very close to what the inverse property satisfies. That is why it is called pseudo inverse actually. Okay. And also remember in a compatibility sense, if A happens to be a square matrix and determinant of A is not equal to 0, then pseudo inverse is nothing but inverse actually, and it is very easy to see that here as well actually. Okay. So, we will end up with a matrix inverse sort of thing actually, that is how it is. Now, before we conclude this lecture, it is also time to see some of this vector matrix calculus in general. In so far we have been talking about vectors and matrices containing numbers, but what if they are functions of some other variable? Okay, so that is where our most interest lies as well, because most of our state variables and control variables, all these are time varying actually. So, if you have a time varying function sitting as a matrix, and then you can certainly talk about their differentiation as well as their integration. And by definition, it simply turns out that if I take component by component differentiation, that is my differentiation of vector x. And if I take component by component integration, that turns out to be my integration of vector x actually. Okay. So, that is simply by definition. But there are interesting algebra after that. So, this is also true for matrix actually. If I have a matrix A which all the elements are time varying, then by definition dy dt of A is nothing but all this the component by component differentiation. Similarly, integration is also component by component, very easy to see that. But after that there are certain standard results again. If I talk about differentiation of A plus B, where A is a function of time and B is a function of time, then it is nothing but A dot plus B dot. That is how it turns out to be. It is very easy to see that anyway. So, all that you have to do here is again go back to this definition. A is nothing but like that. So, A dot is like that. Similarly, formulate B is nothing but B11, B12 like that. So, B dot will be like that. So, add it up. Okay, one side you add up A t plus B t and then take differentiation, use the standard definition. Other side you just add it up this A dot and B dot on the right hand side. You will very easily see that this is very much true, and it feels very much trivial as well actually in a way. So, dy dt of a plus at plus bt by definition, simply you expand the matrix and then put the definition of differentiation, combine it back again, and you will very quickly see that is nothing but a dot plus b dot. Similarly, but this one is very interesting. Remember dy dt or the differentiation of a times b, where a and b both are functions of time. This again satisfies a result that we very closely know in scalar algebra, actually scalar calculus. But the only difference or that careful thing that you have to do here is you cannot change the sequence really. Remember, AB is not equal to BA in general. Okay. The dimensions can be different, AB can be defined, BA may not be defined, and things like that. And A dot and B dot will carry the dimensionalities of A and B along with them simply from definition. Dimensionality does not change. So, obviously, these definitions in a reverse and all that is not defined actually. So, be careful while using this formulation, formulas and all that. It is true, but it is true in the same sequence sense only basically. Yeah. Then this is also easy to kind of derive that dy dt of A inverse is nothing but that. It is again, if you just interpret A as a scalar quantity, then it is nothing but A dot divided by A square actually. Yeah, but in a metric sense, you have to write that way only. You cannot write it that way, and also remember the division of matrices are not defined. So, dA by dt is a matrix divided by somebody writes A square and all that. So, this matrix divided by another matrix is not defined actually. It is simply the multiplication that is defined actually. So, it turns out to be like that, and using this theorem, using this result, it is easy to show that. Just that you have to do is take B equal to A inverse and then carry out this algebra, it will end up here actually. If it is B is A inverse, then this is identity. So, dy dt is 0, and then the right hand side algebra you carry out, then it will be very easy to show that it will turn out to be like that actually. Anyway, so now moving further on calculus, vector matrix calculus really, the gradient vector is something that we will heavily use in optimal control theory, and the gradient is defined something like that, and again depends, see the x can be of n dimension, but function of x, let us assume that it is a scalar quantity. So, a very standard example is something like x1 square plus x2 square plus x3 square like that actually. So, ultimately the quantity is a scalar quantity, but the x vector contains components basically. Okay. So, in that sense the del f by del x is a gradient vector, okay, what it standardly or commonly known as, and that is defined like that. Remember, there is a transpose. So, that is actually by definition we assume that it is a kind of a column vector actually. Okay. This is the gradient vector denoted as del f by del x. It is a column vector with partial derivatives like that. Okay. However, if f itself is a vector, that means x is a vector and f is also a vector, then the gradient vector is not called really a gradient, it is called Jacobian matrix, and this is defined something like that. We just saw that in something like linearization of nonlinear systems and all that. So, you have to carry out all these partial derivatives and then put it in this form, then you will end up with this Jacobian matrix of f of x actually. Then how about second derivative? It's if f of x is a scalar quantity, then the second derivative is defined like this, and remember this is a symmetric matrix guaranteed to be. It's called Hessian matrix actually. Okay, because this quantity del square f by del x1 del x2 is nothing but this quantity actually. So, no matter what order you take, both are same. So, using that property, it turns out to be this matrix is kind of symmetric matrix all the time. Okay, then there are certain derivative rules and all that. See, del x, if it is b is a constant vector rather, and x is a variable, then del by del x of b transpose x or del by del x of x transpose b, it turns out to be b actually. You can think of it as a kind of a scalar algebra sort of thing, but in general in vector matrix calculus also this property is true actually. It is very easy to show that again simply by carrying out the Long-Hand algebra. You take b equal to b1, b2, b3 up to bn, x1, x2 up to xn, formulate this and then take the derivative, use the definition of derivative and then you will end up that it is nothing but b1, b2, b3 arranged in a column actually. So, there is nothing but b vector. Similarly, interestingly, it turns out that the partial derivative of Ax with respect to x turns out to be A, okay, and partial derivative of x transpose Ax turns out to be like that. And as a corollary, if A equal to A transpose, that means this is there, then I can always talk about del by del x of half of x transpose Ax nothing but Ax basically. Just use A plus A transpose nothing but 2A and then it will get cancelled out, this half will cancel out that, will end up with Ax. And this result is something that we will use it heavily later. Okay. So, in general this is true, but if A is symmetric, then this is true also. Okay. Then there are further results which tells you that okay, what if there are two functions like that. So, if del by del x of f transpose g is what, and again satisfies a very close relationship that we know in scalar calculus, but again you cannot change the sequence here. So, this result is given something like this, del f by del x transpose into g of x plus del g by del x transpose into f of x. Okay. And as a corollary, if f happens to be a C vector, then it turns out to be like that and things like that actually. These are standard results coming out of that actually really. Okay. So, remember f and g can be vectors by themselves actually here. Okay. So, many times you use these results also, especially when we talk about this control affine systems and optimal control with that and things like that way. Now, what if g of x is truly a matrix, then what actually, and then turns out like if I have g of x times u, this is where this control affine systems and all will come. I will tell about that as we go along in the course, what is affine systems and all that. But there will be a term something like that, x dot equal to f of x plus g of x times u, that is that kind of a form actually. So, if you have g of x times u and then you have to carry out this algebra, and that is necessary for doing this optimal control analysis and all that. So, then this result turns out to be like that. Okay. And this can be derived like that, where g1, g2 and all are vectors or column vectors coming out of this G matrix. Then you take the partial derivative and put it there in this form actually. Again, these are all long held algebra, it takes about couple of pages, but you can just plug in the standard results from definition and carry out the long held algebra, you will get it there actually. So, as a special case, these things do happen. I mean, if you take only this as a scalar, this is a vector, something like that, and then this turns out to be like this, it is a corollary of all the results that we know. So, what about chain rules then? I mean, if you have function of function, then what actually? So, it turns out to be x is a vector, but f is a function, and then I take another function of that. And then the game starts that okay, x can be a vector in general, but this small f and big f can take different forms. First you take okay, if the small f is a vector and big F is also a vector, small f is a scalar and big F is also a scalar, then this is the result. And if small f is a scalar, but big F is small f is a vector, but big F is a scalar, then that is the result. And if both are vectors, then that is the result. It is very similar, I mean, similar looking, but you have to worry about which comes first and whether there is a transpose or not actually. Okay. Again, these are very standard results, you can have it in somewhere, and then if you want to use it, you can use this in your research proposal also actually. So, that is how I can summarize this lecture, that we have got some overview of what is nonlinear system, and then we carry out what is what is called as linearization of nonlinear systems and all that. Then we talked about various matrix properties that goes along with those matrices actually, and many of these things we will use it subsequently in our further discussions of topics related to optimal control. With that, I will stop here. Thank you.